Last episode, we learned Kafka is a log. This episode, we open the hood and see how that log actually scales and survives failure. Two concepts do all the heavy lifting: partitions and replication. Master these, and you can answer almost any Kafka architecture question. Let's dig in. Start with partitions. A topic, say transactions, isn't one giant log. It's split into several partitions, and each partition is its own independent, ordered log on disk. So a topic with 6 partitions is really 6 separate logs, and Kafka spreads them across the machines in your cluster. Why does this matter so much? 2 reasons, and they're the 2 most important properties in Kafka. First, parallelism. Because partitions are independent, different consumers can read different partitions at the same time. 6 partitions means up to 6 consumers working in parallel. That's how Kafka scales to millions of messages a second. Second, ordering. And here's the crucial catch. Kafka only guarantees order within a single partition, not across the whole topic. Within one partition, messages come out in exactly the order they went in. Across partitions, there's no guarantee at all. Which raises the question, how does Kafka decide which partition a message goes to? That's the partition key. If you send a message with no key, Kafka spreads messages across partitions round robin, maximum throughput but no ordering. If you send a message with a key, Kafka hashes that key and always sends it to the same partition. So here's the pattern that comes up again and again. Set the key to your entity's ID. Use the order ID, or the user ID, or the account ID as the key. Now every event for that entity lands in the same partition and gets processed in order. An order's shipped event can never overtake its created event. But watch out for the hot partition trap. If one single key generates most of your traffic, say one giant customer is 90% of your volume, then one partition, and therefore one consumer, is stuck handling all of it, while the others sit idle. So design your keys to spread load evenly. Now, replication. This is how Kafka doesn't lose your data when a machine dies. Each partition has one leader and some number of followers. The leader handles all the reads and writes. The followers do nothing but copy the leader, staying as up-to-date as they can. The set of replicas that are fully caught up to the leader has a name you must know: the in-sync replicas, often just called the ISR. When the leader crashes, Kafka's controller picks a new leader, but only from the in-sync replicas, because those are the ones guaranteed to have all the data. Let me give you the durable configuration, because this exact trio shows up in interviews constantly. Replication factor of 3, so 3 copies of every partition. Minimum in-sync replicas of 2, meaning the broker will refuse to accept a write unless at least 2 replicas are in sync. And producer acknowledgements set to all. The producer waits for all the in-sync replicas to confirm before considering the write done. Put those together, and you can lose one entire broker with 0 data loss. Replication factor 3, min in-sync replicas 2, acknowledgements all. Say it in your sleep. A quick word on how many partitions to pick, because people obsess over this. 2 rules of thumb. Your partition count should be at least your desired consumer parallelism. You can't have more active consumers than partitions. And roughly, partitions equal your target throughput divided by about 10 megabytes per second per partition. For most high-volume topics, starting somewhere between 12 and 24 is reasonable. And be careful, you can't easily decrease partitions later without breaking your per-key ordering. So don't wildly overcount either. 2 more things you'll get asked about. First, ZooKeeper versus KRaft. Kafka used to rely on a separate ZooKeeper cluster to manage its metadata. Modern Kafka manages its own metadata internally using the Raft consensus protocol. That's KRaft, and it's been production ready for a while now. The interview answer is simply, Modern Kafka uses KRaft. ZooKeeper is legacy. And second, retention. Partitions are stored as segment files on disk, and you control how long they stick around. You can retain by time, by size, or use compaction, which keeps only the latest value per key. And with tiered storage, older segments move to cheap object storage, giving you nearly infinite retention for pennies. So that's the engine. Partitions give you parallelism and ordering, replication gives you durability, and the in-sync replica set is the safety mechanism underneath it all. Next episode, we get hands-on with the two things you actually write code for: producers and consumers.